Hello, welcome to our first video from Chapter 2. This is Lesson 1, using inductive reasoning to make conjectures. Our objective today is to use inductive reasoning to identify patterns and make conjectures, and also find counterexamples to disprove conjectures. If you have not already read Lesson 1 from Chapter 2 of your textbook and filled in the vocabulary on this notes page and in your vocab notebook, now would be a great time to do so. If you're ready to move on, let's start with a warm-up. Please fill in the blank to complete each sentence. Alright, if you need more time, feel free to pause the video, otherwise let's continue. Points that lie on the same line are considered collinear. Points that lie in the same plane are considered coplanar. And the sum of the measures of two complementary angles is 90 degrees. You'll remember these terms from Chapter 1. Now we are ready to continue. Example 1. We need to find the next item in each pattern. You'll notice a pattern here. Please take a few moments, pause the video if you need to, but try and do example 1, A, B, and C. Now, if you're ready to continue, let's see what observations we have. January, March, May. Well, these are months of the year, and you're skipping every other month. We skip February and April, so the next month we would skip would be June, and the next month in the pattern would be the month July. Alright, so write that in. The next one, we have numbers 7, 14, 21, 28. You'll notice that we're adding 7 each time. So if we add 7 to 28, we would end up with the number 35. Okay, you could express this pattern another way. These are the first 4 multiples of the number 7, so 35 is the 5th multiple of the number 7. And then this pattern, we have triangles that appear to be transformed. If you'll remember from our discussion over transformations, these are all rotations. They appear to be rotating 90 degrees counterclockwise. So the next rotation would produce this item, triangle facing this direction. Very good. Noticing these patterns is one of the process that leads us to talking about reasoning. Reasoning is the ability to use logic to make conclusions, to come up with statements about certain things using logic. And so we have two different kinds of reasoning. Right now we're talking about inductive reasoning. Inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. Anytime you collect data and make an observation based on that data, you're using inductive reasoning. All right, and then our next term we need to talk about is what a conjecture is. A conjecture is a statement you believe to be true based on inductive reasoning. So let's look at example 2. I need you to complete each of the following conjectures. The sum of two positive numbers is, well, we know that the sum of two positive numbers would always give us a positive number. This is the word that makes that statement true. The sum of two positive numbers is a positive number. The number of lines formed by 4 points, no 3 of which are collinear, is, well, we need to understand the situation a little bit. So let's show what this would look like. 4 points where no 3 of them are collinear. So we can't put the next one here or here. We'd have to put the third one somewhere else. The fourth one can't be in line with either of these two, so it's somewhere else. So some kind of 4 points in some quadrilateral pattern. So if I connect these points with lines, let's see how many different lines I can come up with. I can connect these two. I can connect these two, these two, these two. But I can also connect diagonally this way and this way. Now, I don't think I can draw any more lines to connect the points without overlapping lines that I've already drawn. So if we count those, 1, 2, 3, 4, 5, and 6, that is our answer. The number of lines formed by 4 points, no 3 of which are collinear, is 6. And the last part of example 2 is part C. The product of two odd numbers is, well, we need to remember what the word product means. The product is the result of multiplication. All right, so if I multiply two odd numbers, then I would get another kind of number. We need to figure out what that is. Well, if we're using the word odd, my answer is probably either odd or even. So let's use some odd numbers, like 1 and 3. What is the product of 1 and 3? If you said 3, you're correct. Let's try 3 and 5, 2 more odd numbers. Well, 3 times 5 is 15. Okay, let's try two odd numbers that have nothing in common with these two. Let's try the number 7 and the number 11. Well, 7 times 11 is 77. As you notice, every product ends up with another odd number. And so the product of two odd numbers is odd. Let's move on. In example 3, we're going to make our own conjecture. You previously just were able to complete a conjecture, but now we are going to use these data observations about the average whale lengths of male and female whales, and we're going to make our own conjecture. So let's look at this first. We have these different measurements in feet of female whales across the top: 49 feet, 51 feet, 50 feet, 48 feet, 51 feet, and 47 feet. Those could be compared with their male counterparts: 47 compared to 49, 45 compared to 51, 44 compared to 50, 46 compared to 48, 48 compared to 51, and then 48 compared to 47. Now I would say this one is the only one that's a little bit different. But in all the rest of these measurements, what do you notice? You might have noticed that the male measurements were shorter than that of the female counterparts. So we could conclude that in general, the length of female whales is longer than that of male whales. So we could write a conjecture like this: female whales are longer than male whales. That is based on the inductive reasoning using these observations. Now, to verify the truth of a statement or a conjecture, there's some processes that have to happen. For right now, we're going to look at how to disprove a conjecture. And we do that by using a counterexample. A counterexample is an example that proves a statement to be false. A counterexample is an example that proves a statement to be false. A specific example shows you one case where something could be true, but a counterexample is a way of showing that a statement is completely false. If you can think of one way for it to be false, then you cannot say that the statement is true. So this is our process for inductive reasoning. Step 1 is to try and notice a pattern. Look for a pattern. Step 2 is to make some sort of conjecture based on that pattern. And then step 3, either prove the conjecture to be true, or if you're trying to say something is false, find a counterexample that helps. So let's look at example 4. We're going to do all 4 pieces of this one at a time. Let's show that each of these conjectures is false by finding a counterexample. So here's our first one. For every integer n to the third power is positive. Well, integers, if you'll remember, are the numbers on the number line. -3, -4, 2, 7. Those are all random numbers that are on the number line. So if I think of an integer, one of the easiest ones to use is the number 1. Then n to the third is said to be positive. Well, let's test that. If I use the number 1 for n, then n to the third would equal 1 to the third, and that is 1. That's positive. Well, since we're talking about positive, a counterexample would be an integer n that would result in a negative number when taken to the third power. Well, that means I should probably try an integer that is negative. If I said n is -1, let's try that. N to the third would be -1 times -1 times -1. -1 times -1 is +1, but -1 times +1 is -1. There's our counterexample. If n is -1, it's an integer, but n to the third would be -1. That would be not positive, but negative. So we would write our result this way: false, and then put a comma to show that we are giving a reason for it being false. If n equals -1, then n to the third equals -1 as well. That's our counterexample. So let's try some of the rest of these on your own, and we'll check our answers. If you need to pause the video for more time, go ahead and do so now. All right, hopefully you had a chance to look at these. Let's try this one. Two complementary angles are not congruent. Well, I can think of two complementary angles that are congruent to prove this wrong. Complementary angles, remember, add up to 90 degrees. So two angles that are going to add up to 90 degrees that are congruent, the same measure, could be 45 and 45 degrees. There's your counterexample. Part C, for any real number x, x squared is greater than or equal to x. This one can be a little bit tricky. If you just think of real numbers as the numbers 1, 2, 3, 4, 5, 6, 7, those are actually the counting numbers, and this would still be true for that. But we have lots of other real numbers to consider. Let's consider the number 1/2. If x equals 1/2, then x squared would equal what? That's right, x squared would equal 1/4. 1/2 times 1/2 is 1/4. In this case, 1/4 is actually less than 1/2. So this is our counterexample. All right, supplementary angles. You might remember supplementary angles are angles whose measures add up to 180 degrees. It says they are adjacent. Well, if I can think of supplementary angles that are not adjacent, then I've gotten a counterexample. So we could have something like this. These two angles would add up to 180 degrees. This angle measures about 150 degrees. This one is about 30 degrees. Those add up to 180, but they are not adjacent. So that is your counterexample. All right, we have one last statement, and this refers to the given information here. The radius of every planet in the solar system is less than 50,000 kilometers. So if I can come up with a measurement for a planet's radius that is greater than 50,000, that would be my counterexample. Well, Mercury, that is less than 50,000. Venus, less than 50,000. Earth, less than 50,000. Mars, less than 50,000. But as soon as I hit Jupiter and Saturn, I have measurements greater than 50,000 kilometers. You do not need to list both. You just need one counterexample. So we could list our counterexample as Jupiter. All right. Jupiter has a radius of 143,000. You could also say Saturn, but you only need to say one or the other, not both. Well, I hope you've been able to understand the material a little bit better. If you have more questions, feel free to ask in class. You will have the assignment given to you in class, or you can also find it on the Edmodo post. Thank you very much, and hope you understand inductive reasoning a little bit better.